Here we have a classic train travel distance equals rate times time problem. I'm going to show you the sort of precise, slower way to do this problem. We'll talk a little bit about the intuitive way to do this problem in a few minutes. But basically the problem looks like this. You have train A going west, let's say, and train B going east. So if we say this is train A and this is train B, we can write that the distance train A is going, using a subscript of A, is the rate train A is going times the time train A times the time, times the time train A spends traveling, and the distance train B goes is the rate of train B times the time train B is going. Now, formally what I'm doing is I'm writing distance equals rate times time about each trip or section of a trip or leg of a trip that anybody is traveling. If you use this method, you'll be able to solve any distance equals rate times time problem, assuming that you can write the connecting equations. There are easier ways to do this problem, as I've mentioned, but right now we're going to connect these things and fill in what we know. So if you use these subscripts and write the equations like this, filling in what we know that the time for each of them is the same. That is, T sub A equals T sub B equals 2 hours. And we also know that one of their rates, and we'll just assume that it's train B. So train B is the speed of train A plus 15. In other words, it's 15 miles an hour faster than the other. I picked train B only because I've drawn it so that it looks like train B has gone a bit further. The other connecting equation is that the two distances added together is 230 miles. This is our connecting or main equation. What we do at this point is we'd substitute in everything we know and replace D sub A with R sub A times T sub A, except T sub A is just 2. So we're going to replace this with numbers that we know into there and take this and replace D sub B with numbers that we know. So that's going to give us R sub A times 2 plus R sub B, but R sub B is just R sub A plus 15, also times 2. Be careful that you put the parentheses in because the whole velocity of train B is multiplied by 2 hours, and that's going to be a total of 230 miles. What we now have is one equation with only one variable. If we rewrite this cleanly and distribute, we should get 2R sub A plus 2R sub A plus 30 equals 230 miles. We subtract 30 from each side and collect our R sub A's. We're going to get 4R sub A equals 200. Divide each side by 4, and we're going to get that R sub A equals 50 miles per hour. And of course that means R sub B, the speed of the second train, is going to be 15 miles an hour faster than that, which is 65 miles per hour. So the speed of the two trains are 50 miles per hour and 65 miles per hour. Now, let's see if that makes sense. If you go 50 miles per hour for 2 hours, that's 100 miles, and 65 miles per hour for 2 hours, that's 130 miles, and 100 miles and 130 miles is a total of 230 miles. So obviously another way to do this problem might be to say, gosh, if they're going to travel for 2 hours, let's just divide 230 by 2, and we're going to get 115. And that means their two speeds have to add up to 115 miles per hour, and one's 15 miles per hour faster than the other. So if you subtract 15 off that, you should get twice the slower speed, and of course that's going to be 50 miles per hour. So you can kind of reason your way through these in a fairly straightforward fashion. The challenge is when the relationships get a little more complicated, as we will show in the next slide. And you know, it then turns out to be useful to break things down into very detailed distance equals rate times time about each trip and see what happens after that. Here's a second distance equals rate times time problem. What we're going to do is we're going to sketch this one out as well. And what this means is Julie started here, went for 70 miles an hour for a while. So we'll say 70 miles per hour. And then got a ticket right here. And then drove for 60 miles an hour the rest of the trip. And the entire distance was 255 miles. So 255 miles total. So if we write distance equals rate times time about each section, we can write that distance going 70 miles an hour plus the distance going 60 miles per hour equals 255 miles. And the distance going 70 miles an hour is the rate times the time, so it's 70 times the time, and we'll call it t sub 70, plus 60 times t sub 60, and that equals 255. Now what we need is a connecting equation, and the connecting equation, of course, is that the time spent total is 4 hours, so t sub 70 plus t sub 60 equals 4, which means we can replace either one of those with 4 minus the other one. So let's replace t sub 60 with 4 minus t sub 70. In other words, t sub 60 equals 4 minus t sub 70, and we'll replace that. So we're going to get 70 t sub 70 plus 60 times 4 minus t sub 70 equals 255. If we distribute and clean this up, we're going to get 70 t sub 70 minus 60 t sub 70, which is 10 t sub 70, plus 60 times 4, which is 240, equals 255. If we then subtract 240 from each side, haven't left a ton of room, but that's going to get us 10, and I'm just going to write t, but, well, actually I'll write t sub 70, equals 15. Divide each side by 10, and we're going to get t sub 70 equals 1.5 hours. So it says that she spent 1.5 hours going 70 miles an hour and the other 2.5 hours going 60 miles an hour. So let's see if that makes some sense. 2.5 hours going 60 miles an hour is going to be 120 plus 30 is 150 miles. So this turns out to be 150 miles. Okay, and 70 miles an hour for an hour and a half is 70 plus 35 is 105 miles. And that does indeed add up to 255 miles. There you go.